It's not though.
So, our last topic of this unit is going to look at a substance that's slightly harder to find the pH of. It just adds an extra step, and that is salt. If you're given a salt, which of course is just an ionic compound, a cation bonded to an anion, finding the pH of it takes a little extra thought. And in order to do it, we're going to do a process called hydrolysis. So, today we're looking at how to find the pH of salt solutions instead of the pH of just strong acids or weak acids. We're looking at salts. And the way that we're going to do this is we're going to make some assumptions about how salt is created. Now, this is just a coincidence, but usually when you say salt in high school, that's the compound that comes to mind. But remember, by definition, salt is any ionic compound. All right, this is just table salt that many of y'all have consumed today. Now, if you remember, salt is created through neutralization. A neutralization reaction was an acid reacting with a base to produce salt and water. That should sound familiar. So what we can do, if I were to say, hey, I'm going to add NaCl to water, what's that going to do to the pH? Well, it's not as easy as when it's an acid or a base, right? If I were to ask you what's that going to do to the pH, you'd be like, well, I don't know how that interacts with H's and OH's and stuff. Here's how you do it. We want to think about the parents that created NaCl. All right? Did they like each other? Did they go on a lot of dates? Was it just a prom thing? Don't make prom last forever. Anyway, if we think about the parents, which is really doing a reverse neutralization, I can assume that the Na had a parent of NaOH and the Cl had a parent of HCl.
Oh.
All right?
Okay.
So, knowing that the OHs and the H's are the driving force behind the neutralization anyway, I know that these were the parents. And then you can analyze the parents to guess what pH will do. Is NaOH weak or strong? That's a strong. It's hydroxide to a group 1 metal. All right? Is that's here? Let me not do that. It makes you think it's solid. All right, strong. All right, is HCl weak or strong?
Strong.
I bring clay. Strong. All right. If both parents are strong, what can we assume about the resulting pH?
It's going to be
Equal to 7. Neutral, as the screen says. Let's do another one. All right, let's take a look at ammonium nitrate.
Oh, it's pretty basic stuff.
Ammonium, that will not happen in high school. Ammonium nitrate, all right? Again, if I asked you, hey, is this going to do, what will this do to the pH? You cannot tell as easily as you might have been able to, just in general. Is it going to make it go up or down is all I'm asking, not for a number. You can't conclude maybe as quickly as you could in the other lectures. So what do? Let's take a look at his parents. All right, the NH4 would have had a parent of ammonium hydroxide, while the NO3 would have had a parent of HNO3. This is our second example. Oh no, I don't have my examples up yet. I mean, here you can trade slides if you want. I thought it was better with this slide up, but I mean, right now I'm finding the pH of ammonium nitrate. Now we already did sodium chloride. Hey, ammonium hydroxide, weak or strong?
Weak.
That's weak. All right. Nitric acid, weak or strong? Strong. Hey, look, this one's different. All right. Here, the acid wins. All right, because strong is going to beat weak in terms of pH. So then what would we generally expect the pH to do if the acid wins? We would expect the pH to be less than 7. Because it was a typo, I'm sorry.
If you know that one of them's weak, you can just say the other one's strong.
No, because the moment it, yes, in this class, yes. I didn't think enough about the
Wait.
phrasing of your question.
It's below 7.
The pH.
Oh.
The pH will be lower than 7.
Because
The acid wins, and we know that's the connection. All right?
So if it's the base one, it'd be
Above 7.
above 7.
Right, yeah. All right, so this is the extra general thought you want to have to figure out how a salt will affect the pH. Now, why? Why specifically is this true? Well, I want you to be able to analyze that as well. So let's do one more. All right, now it's going to have us do sodium carbonate. So sodium carbonate is Na2CO3. All right? Now, we can draw the same conclusions, right? I can assume that the Na started off as NaOH. I can assume that the CO3 would have had a parent of H2CO3. I could also say that I know this dude here is strong and that this guy here is weak. Does anybody not know anything, have a question about what I just did?
I do have a question. Are bases always on the left and acids always on the right? Or
Yes, because we're always going to be connecting the negative hydroxide to the cation of the salt, and the positive hydrogen to the anion of the salt.
The reason why it's weak is because there's 3 O's and not 4 O's, right?
Exactly. In that case, there's only one more oxygen than hydrogen, so it's all right. And it contains carbon. Yeah, it's a double whammy there.
Oh yeah, true, yeah.
All right. So who wins? Well, check it out, y'all. The base wins.
Oh, I see, so.
All right. So if the base wins because strong will beat weak, what do we know immediately about the pH?
pH will be above 7.
The pH is going to be greater than 7. All right? So look at all these conclusions we can draw by just being given salt. But I said I wanted to go a tad further and show you exactly what happens for the pH to go up. All right? And this is what is called hydrolysis. What we're going to do in order to analyze this is we're going to take whichever of the ions is weak and add it to water. The word hydrolysis should make you think of water. But before I show you what the right thing to do is, I want to show you why you can't do what's considered the wrong thing. So do write this. I want you to analyze it. But again, the right thing is going to be to add the weak ion to water, not the strong ion. Because it turns out if I take this strong ion and I add it to water, there will be a no reaction. Therefore, the strong ion will show up on the other side. What is the vocab word for when something is the same on both sides of a reaction?
Single replacement.
it's not equal.
Oh, it's something.
It's a spectator ion. Remember when we were doing net ionic equations? Whenever something was the same on each side, we kind of ignored it because it was a spectator ion that was doing nothing. So my point is, in these hydrolysis problems, the strong ion is always a spectator. I don't know if you'll ever have to conclude that on the AP exam, but it is within our scope, so I want you to know that, all right? The strong ion is a spectator ion. Yes, question?
So, why is there no reaction?
Because there's just not. If you add sodium to water, if you add the sodium ion to water, it's not going to hydrolysize.
Yeah.
All right?
And then could there ever be a weak?
There can, not in high school.
Wasn't that an intermediate?
This isn't a mechanism. The mechanism would have to have multiple steps. Okay, so what's the right thing to do then? The right thing to do is to take the weak guy here. So the weak ion is CO3 minus 2, all right? And we're going to add him to water. And when you do that, you're going to have a Bronsted-Lowry, and now everything we've been working on in the unit comes into play, and life is as expected. All right? So when this happens, my CO3 is going to be accepting an H. That's going to make him HCO3 minus. And then, of course, he got it from the water, got it from his mama. Well, we're talking about parents, so it kind of fits. All right? And here's what I've done, guys. I've proved why the base wins. Without doing this, we knew the base was going to win, right? But look at what's in the solution. Look at what is floating around in the solution. Hydroxide, which is the substance that best defines a base. So it's two ways of showing the same thing. Why am I giving you this well-rounded idea on what's happening at both kinds of levels? Because I don't know I don't know how they're going to ask the questions. All right, they could ask it on a very simple, will the pH go up or down? Or they could ask the very simple, how come? In which case they might want you to justify it with an equation. Whichever ion is weak gets added to water, and then a Bronsted-Lowry takes place.
Oh, okay. So whenever you add weak acid to a base.
Right, but that's what we did in our last lecture, right? The only time that we did the Bronsted-Lowry was when it was a weak substance.
So what you need to know about for Schoology, water part?
Oh, yeah. If I cover it in class, it's absolutely Schoology worthy. Okay. All right, so let's practice this. I don't want it to be crazy. Let's look at a couple examples. All right, so it wants us to do the same thing with potassium cyanide. So let's go KCN. All right, we're going to do the full analysis. I want you to stop me if I do something that doesn't make sense. All right, first off, I know this is salt because it's made up of a cation and an anion. All right, really, the fact that there's a metal in there is one of your big determiners. All right, they don't always have a metal, but most commonly they do. So we've got our metal there bonded with a polyatomic, so it must be ionic, must be salt. Hydrolysis is necessary. So what I'm going to do is I'm going to say, well, this parent would have been KOH. This parent would have been HCN.
You're worried about charges and that stuff?
No, not here. The charge will only happen while it's dissociated. All right? So here, my potassium, my KOH, weak or strong? Strong. All right? And realize that if you don't know your weaks from your strongs, it's already game over, right? So make sure you know that. All right, what about my HCN, weak or strong? Weak. It's a carbon-containing acid. Robin.
How do you decide which one gets the OH?
Because you're just, since this is plus and minus, all right, in my ion, and my H is plus and my OH is minus, it's an electrical attraction. So the OH has to go to the cation, the H plus has to go to the anion. All right? Hey, who won? Hey, we got a base winner. KO. All right. Base wins. If the base wins, we can already predict that the pH is going to be
More than 7.
above 7. All right. And a lot of the questions I expect to all be answered by what we've done so far. All right. So hopefully so. That's all conceptual. All right. And then what are we supposed to do to prove it? All right. Yeah, a Bronsted-Lowry, where we're going to take the weak ion, which was Cn minus. There's the weak ion. We're going to add him to water. And you know what? Here's what I do, and it'll help you on the future problems. Stop for a second. I know I keep using the phrase prove it. I don't want to mislead you to think that you're going to get something weird over here that disagrees with that. And you're like, oh, it's a hard one. No. If you know that you did this part right, then you're absolutely right that the base is going to win. All right? This isn't going to steer you wrong. But if I have already concluded that the base is going to win, I know one of my products is hydroxide. And that's absolutely true. So instead of sitting here and getting stuck on the next part, and maybe I don't want to confuse you. If you don't like what I'm saying right now, this is what I did in college. I would know one of the products based on who the winner is. All right. Hey, what would I have put there if the acid one?
An H plus.
Hydronium. All right, H3O because we're altering water. So it would be H3O plus. I know is one of my products. I don't have absolutes that I get to give y'all very much in here. This is an absolute. If the base wins, hydroxide is a Bronsted-Lowry product. If the acid wins, hydronium is a Bronsted-Lowry product. So what's the other one? Well, for the OH to form, he had to give away an H. HCl. And there's our proof. All right, what was the whole point of that? It was simply to prove that when it's all said and done, our solution is containing OH minus, which will always make the pH be above 7.
Is the other equation or whatever at equilibrium? Is that equilibrium?
This is equilibrium because it's a weak sample. Weak samples are always at equilibrium.
Weak sauce.
Is it acid with
H3O plus.
Mr. C, do you use more H3O plus or H in your assignments?
Well, they're completely interchangeable. But if it's Bronsted-Lowry, it has to be H3O plus.
Still the same, right?
It's the exact same thing. In chemistry, it's the exact same thing because they're constantly bouncing between each other and water. Okay, let's do the next one down. By the way, guys, I totally anticipate that I'm going to be recording after y'all walk out the door because of what happened last period. So expect the bell to cut me off and me to just keep going. So when that happens here in a while, you're, of course, welcome to leave or stay, whatever. Okay.
Yeah, we get out at 51.
I know it's not time. I know.
I'm scared of this teacher next period. I think I want to stay.
Anyway, so hey, our next one is methylamine chloride. That sounds exciting. Hey, it says write the dissociation equation. So let's make sure we do what it says. All right. It wants us to write the dissociation equation. So CH3 NH3Cl.
It's solid though, not
No, that doesn't matter. It's just starting solid. It'll be aqueous. And it wants us to write a dissociation equation. Now remember, that's where we just break it apart into its charges, right? So the methylamine is the CH3NH3, and then of course chlorine is the other ion there.
How are we supposed to know that later?
So that's why I went back and wrote it, because I know that you are not very aware of methylamine. On the AP, they're going to be far kinder than some of these questions that I dug out. But if you just look at the way the name is written, it kind of pushes you towards ionic, because it's that two-word. You know, chloride is a negative ion. All right. So sometimes recognizing the salt is the more challenging part. We're going to. I'm just doing what it said. All right. So I'm starting with the dissociation equation. All right. But when we add it to water, we're only going to care about one of the parents, not both of them, because one of them is spectator. So I don't want to waste my time with the spectator ion. Now, what I can see right here is a nitrogenous compound. All right. But it's the Cl that we definitely know. I mean, look at his charge. We know that Cl is the guy that's going to bond to the H. What do we know about HCl as a parent?
He's strong.
He's strong.
He's strong. Oh, yeah.
I bring clay, right? All right. We know that the nitrogen is a big indicator of weak. All right. Therefore, we know that the acid wins. All right. So we know the pH will be below 7. My bad. All right. So now we can write the equation, the hydrolysis of the weak ion. All right, and that's why it had us dissociate it, so that we can easily pull the entire ion to add it to water. But it won't always make you do that. I mean, once you get comfortable, don't do more than you have to do to still get a completely right answer. So I'm going to take that ion. I'm going to add it to water. Hey, but since I know the acid one, what must be a product? H3O plus, right away. All right. Again, you can just do the Bronsted-Lowry as we've been doing, but I like this connection. I've always liked it. I feel like it makes I feel like I think less because of it. All right. So for that to form, we know that an H needed to be donated over to water. So we're going to end up with CH3NH2, no charge. The question wants us to also do an equilibrium expression. I mean, we can do that. It's really easy. There's no math here. But of course, it would be the H3O plus times the CH3 NH2 over just the CH3 NH3 plus.
Should we do that anyways? Showing the point.
Yeah, but the only thing is that since there's no math to run showing the unsubstituted equation, there's not really a call for it, because the unsubstituted equation is always really good because it proves to the graders that you're about to put the numbers in the correct way. Even if something goes wrong, they'll usually still give you a point for that. But there's no numbers. There's no numbers. Kind of just stops there. How do we feel? So, before I apply hydrolysis to a more standard problem, I want to summarize the unit for you real quick.
Okay.
So, here's what you definitely want to walk into Thursday's test knowing. All right? And this is just for pH. It's not just this. You need to make sure you know everything from Monday, which was a bunch of acid-based stuff. This is for the unit. Yeah. Well, this is just pH calculations. I'm just doing a differentiation here. To find the pH of a strong acid or base, it's just negative log. To find the pH of a weak acid or base, it's a Rice table. To find the pH of salt, it's hydrolysis, and then a Rice table if you have numbers. We haven't had numbers yet. We're about to. Yes, the equation. All right, so we have two problems that I want to do, and again, I don't think I'll get to finish the second one in time, but we will anyway. So let's take a look. Hey, will you cover up that bottom part, just the wordy part?
Oh my
All right.
gosh.
I'm covering up the part that tells you how to do it because I don't want you to be reading that and comparing my work. I'm going to do what it says, all right? But I want you to just be focused on what I'm doing.
It's fructose.
What? That is not fructose.
I thought you said Fritos on there.
Hey, it's acetate.
My believe in biology.
Okay. Now, this question should look like questions you've been answering. The difference is the compound. All right? It's salt. You see the metal there? Do you see the metal that's starting that compound? All right? It is sodium connected to acetate. It's a bonding polyatomic. There's a bunch of things here that are pushing you towards it being salt. All right? But when I know it's salt, there's some stuff I know to do. So we've got NaC2H3O2.
Are those two separate questions?
No, this is one question. Here, I mean, what, this down here?
No, the K, what's all that?
It's giving you information. It's giving you standard info. So, okay, well, what do we need to know about a salt? Well, we need to look at its parents.
It's illegal.
We know that sodium's parent would be NaOH.
No.
We know that acetate's parents would be acetic acid. All right? I know that this is strong and that this is weak. Hey, what's the special word to describe the strong ion?
Spectator.
It's a spectator ion. Forget him. He's trash.
I think I'm gonna make a song to identify bases.
Anyway, what?
How do we know that it's so?
Oh.
Because by definition, the strong ion is a spectator ion. It won't hydrolyze, all right? What does undergo hydrolysis is the weak ion. So let's take the weak ion, and here, check this out. Oh no, that looks terrible. Now, why am I going Rice?
No.
Because lunchtime.
Isn't it
Be-
Rice?
Yeah, I'm pretty sure. Yeah, why is there an R there?
We're going rice because now we have values, right? Now it's math. So let's get our reaction ready. Let's take the weak ion of C2H3O2 minus and add him to water. Hooray, hydrolysis. All right. Hey, look who won, guys. The base one, OH minus, is definitely one of my products. All right. And then, of course, Bronsted-Lowry, to get there, we needed to have this H head over here. All right. And now that's where we've been stopping so far today, because it proves that the OH negative is what's making the pH go up and blah, 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 blah. But now this wants to know what the pH is. All right, we know if it's below or above 7, whatever. What is it? Okay, well, I've taught you how to do that.
Okay, so
So here we go. We've got 0.7 molar to start off with. And we have no starting concentration of our products. We want to show our expected shift. I plus C equals E. Now I'm about to have to start doing a bunch of board sliding, and I'm sorry. Now, here's the annoying thing. We know that during a rice table, there's a bit more information given to get us going. What is the extra info here? It's Ka. Now, the reason they're giving you Ka, look, listen to this. The reason they're giving you Ka is because the ion that you're analyzing came from an acid. Do you agree?
Yeah.
That's why it's Ka. But in these problems, the product that you're connecting to is not going to be connected to that acid. It's always going to be connected to the other guy, which means the Ka is not usable to find X. What do I need to find X? I need Kb. And that will always happen in hydrolysis. Now, you already know how to change it over. We've been doing it all week, all right? But you can't not do it. So listen again. They will always, in a hydrolysis problem, give you the wrong K, because they have to give you the wrong K based on what you're analyzing. Now, this tells me that the Ka is 1.8 E negative 5. All right? But we said that to find the OH concentration, well, that requires a Kb, of course. But the conversion is so simple because you know that Kw divided by Ka equals Kb. Or vice versa, Kw divided by Kb equals Ka. It's always true. Kw is our favorite constant value of 1.0 E negative 14. So in other words, we're going to go 1.0 E negative 14 divided by the given Ka of 1.8 E negative 5, and that will give us a Kb of poo. Okay. 1 E negative 14 divided by 1.8 E negative 5. I get 5.6 E negative 10. Yes, ma'am. No. The value for Kw will, but the idea on how to convert between the two will not be directly shown. Now, what will be shown, here's what is shown though. It'll say Kw equals H plus times OH minus, which is Ka and Kb. So you can manipulate that to get that very easily.
Just clarifying, Ka is acid and Kb is base.
Equilibrium of an acid versus equilibrium of a base. Well, that's just the equilibrium of the concentration. is what that's supposed to be. But, all right, back up here. We're still rocking and rolling. So, hey, we got rid of that Ka because we don't need him. Because, look, our X is going to solve for OH minus. That is Kb. And now we can go for it. So, let's go. 5.6 E negative 10 is the K equals X squared. Those are the products. Over 0.7 minus X, the reactants. Now, notice I didn't write the unsubstituted equation. I love you. I'm sorry. If I do, there will be no board space. You be better than me. You be better. Be better than me. All right? Some of you like this expression over 1. All right? Whatever, but we need to cross multiply. If we do, we'll get X squared equals, I need to distribute 5.6 E negative 10 times 0.7. I get 3.92 E negative 10. All right, minus, distribute to the X, 5.6 E negative 10X. Again, stop me if I do something weird. Let's reorganize because it must be a 0 equals. So let's go 0 equals X squared plus 5.6 E negative 10X minus 3.92 E negative 10. Let's go solver. I get 1.98
That's not right.
E. Whoa, never mind.
I got 0.
I got
1.74.
2.0.
Hey, what did we get? What? I got 2.0. What'd you get?
I got 5.
Did I mess up?
Now, hey, if you get a negative number,
I didn't. Thank God.
it must be, there it is.
Wrong.
No, take absolute value. You're fine if you get a negative number. Yeah, I got 1.98 E negative 5.
Where'd the bird
I
go?
got 2.
I got 2.
What the hell?
Oh.
Wait, but did you guess? Did you click 2 and then solver?
No, it like came out to 2.0.
Oh,
Yeah.
on her.
Yeah.
You did not get this.
No. I got 2.0.
I don't know why she did that to me. I don't know why she did that. That is my song. That is my song. I stand by that song. Big Boy Diamonds.
Is it like
try typing it into.
Is it Mr. Cummings?
It's cutting off. See, it's rounding. Your calculator's rounding.
Okay, you're fine. Wait, is it not negative?
I got 1.
No, it's absolute value. The number's fine. Take the absolute value. Now we're not done, so I need to catch y'all back up.
Wait, so
guys,
if it
listen,
was
guys.
This is not the answer to the question.
if this was a positive, would it be a negative?
No. Absolute value makes everything positive.
Oh, I see. I searched it again.
So no answer.
Robin, did you get it?
No. Kind of. I got 1.97 now.
Okay, but what's the next number? It's not showing you another number? All right, sweet. Now,
Great.
hey, what did we find?
So what did we
No, it's there.
Look what we found.
The OH.
The OH concentration. So we've got the OH concentration, all right? So then this is a molarity. All right? What does it want us to find?
pH.
What is the pH? All right, well, there's still work to do. And this is why I told you, make sure you keep your bearings in the problem. I see how annoying this is, all right? The class is amazing. But keep track of where you are, because you don't want to get to X and be like, it's a good number, but I have no idea what it is, all right? It's the OH concentration. Well, if we want pH, we need to first get the H concentration, all right? In order to do that, well, we know that Kw 1E negative 14 divided by that number is this number. So let's go 1.0 E negative 14, that's Kw, divided by the molarity that we found, 1.98 E negative 5, and I get an H plus concentration of 5.05. 5.05 E negative 10.
How did you do all
Wait, so like last time?
All right, so to get that, I was saying it, but some of y'all didn't follow me. So I went Kw 1.0 E negative 14 divided by the OH concentration, 1.98 E negative 5, and that gave me the pink number because Kw divided by OH is H plus and vice versa. Because the 5.6 is a constant value. Ka and Kb are constant values that don't dictate sig fix.
So that just be 5.05
E, no, that's the H plus concentration. How do you find pH from an H plus concentration?
Subtracted by 14. 10.
Negative log. Negative log of a molarity is pH. So now,
Wait, what was the answer?
so finally, we want to go negative log of that concentration, 5.05 E negative 10, and that will give us a pH of 9.297.
Wait, why is it worse?
It's not. That's 3 sig figs. A pH only counts sig figs to the right of the decimal. Yeah! Friday, am I right?
Friday.
No, we did so good at our teamwork.
Now, I'm going to start another problem for the video for sure, but even if you are checked out because I know it's exhausting, you've got to stay quiet to respect what I'm trying to do up here. All right? Can you show the next slide for me? But I can see it. Okay. So, there's 2 more problems in the lecture. There's an A and a B of doing the same type stuff. I'm going to do A from scratch, which is the potassium hypochlorite. Again, I totally invite y'all to work with. What time do we get out of here? 51. Oh, that's 5 minutes of amazingness. Okay, so it wants us to find the pH of an obvious salt. It's an ionic compound. It gives me KClO. So we've got KClO that we're analyzing. Right away, I can tell that we've got KOH versus HClO. All right? Based on that information, we can tell that this guy is going to be strong and this guy is going to be weak. All right? Now we're doing that because it's salt. We only do that because it's salt. So now we can move forward into taking my weak ion and hydrolysizing it. So my weak ion was ClO minus, and we want to add him to water. Okay? I know that my base is winning OH minus, but if you follow the Bronsted-Lowry, you'll see that we have a donation here to make him HClO.
Why did you take out the H from CLO?
because it's just the weak ion that's going in. Remember that H is not actually there. The salt that we're analyzing is the KClO. It's just to identify the weak in my mind, because this isn't even a part of the chemistry really. This is what you're thinking to figure out what the weak ion is. All right, but that was never there. That was the parent of the creation of that salt. All right, so now it wants us this time to calculate pH. I should have done the other one. That would have been quicker. But anyways, whatever. We'll keep doing the annoying problems. So there we go. We're ready to go. It looks like we've got 0.355 as our molarity. So 0.355 was my initial molarity. All right. My shift is as expected. All right. And then we're going to add I and C. Now, as expected, since it's a hydrolysis problem, I can see, not as expected. If you look at the very bottom, do you see what the italices say? If the problem doesn't give you the Ka or Kb, you can go and look it up because, like I said, they're constant values. Now, I'm just going to give it to us, but there might be a problem or two on Schoology that you get to this part and you're like, holy crap, what do I do next? I have no more numbers. All right? Go and find the missing value of your ion there. All right?
Is that going to happen in a test?
No, they can't do it to you on the test. I mean, they obviously can't do it to you on the AP for sure, but no, because if you open up Google while you're taking my test, I get unhappy. So don't do that. No, I'll give it to you, but just because it's common chemistry practice to have to go and reference something somewhere else, your Schoology might habit that of you. But anyways, I went and looked it up, and it is somewhere in my notes, but not there. Sorry, now I'm embarrassed. 3.5, so we have a Ka of 3.5 E negative 8.
Wait, how did you?
All right? But as always expected in hydrolysis, that is not a bueno number because what we're going to be finding is OH, which has no connection to Ka. I must have a Kb. In order to convert your Ka to Kb, it's always your Kw, 1E negative 14, divided by the Ka gives you Kb, the Kb gives you Ka. So we're going to type it in. I'm going to go 1.0 E negative 14 divided by the number I went and found on a table somewhere, 3.5 E negative 8, gives me my Kb. And in this case, come say hello to the people. This is a student. Okay. I get 2.9 E negative 7. And now, what's that? Oh. Now the Kb is the usable number, and now it's just equilibrium, blah, 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 while we keep track of what we're finding. So, if I take that Kb, all right, and
Quick question, Mr. C.
Yeah.
Why is it that we can't use Ka?
because Ka does not have the ability to give an OH concentration. Ka can give a hydronium concentration. All right, and these will always mismatch because of the source of the ion. All right, so unsubstituted equation should just be Kb products over reactants, no numbers. When you substitute it, you're going to go 2.9 E negative 7 equals my two products, x squared, over my reactant, 0.355 minus x. All right, and now we're good to solve. All right, if we cross multiply, we'll get x equals, we need to distribute here. So I'm going to go 2.9 E negative 7 times 0.355, and I get 1.03 e negative 7 minus this value times x, 2.9 e negative 7x. Your solver wants this as a 0 equals, so we'll move the variables and end up with 0 equals. Oh, I never hit record. I'm just kidding, that would suck, right? I love you kids for still hanging out. All right, that would equal x squared. All right, we'll move it around plus 2.9 e negative 7x minus 1.03 e negative 7. And then we got to go all solver happy.
Yeah, I love how now that everybody's gone, you're actually chilling. Because before I like.
He gets a like.
Yeah, that's pretty.
Oh, am I more relaxed now? I don't know. Okay. X squared plus 2.9 e negative 7x minus 1.03 e negative 7. All right. Can anybody out there in the world
I get it.
verify my answer?
3.21.
Yay, that is it. All right. But there's a scientific. Hey, it's scientific. It's hiding in the decimals.
What?
It's a scientific value. It's not 3.21. It's 3.21
Oh.
e negative 4. So
Okay.
careful.
I knew that, but I'm saying I was get the answer.
X equals.
Oh yeah, I knew it was even 4.
Where did they get the sig figs again?
I mean, we're going from our starting value 3 sig figs. That's a constant value.
Oh.
So the K's don't contribute. So I've got 3 sig figs running through. All right. Wait, it was 3.21. Is that right?
Yes.
Okay, cool. And so that is molar. Now, here we go. Here's where it's, what the heck did I just find? All right, we found X. X is the concentration of hydroxide. Now, you are going to run into problems that want the concentration of hydroxide. Just read carefully. If that's the number it wants, you're done. Or maybe it wants POH. Well, that's great. We can take the negative log to get POH. Of course, I'm as annoying as I can be, and we want pH, which we can't get from OH. So, here we go. To get H+, we've already done this once with different numbers, but we know that KW divided by H+ is OH minus, or KW divided by H+ is OH minus. I say the same thing twice, I hope not. So, awesome, I'm good at this. Okay, so we're going to take our KW of 1e negative 14, 1e negative 14, divided by this concentration we just found, 3.21 e negative 4, and it will give me the concentration of the hydrogen there of 3.112 e negative 11. Now, finding the pH, after all of this, so easy. Negative log of the concentration. So I'm going to go negative log of 3.12 e negative 11.
But don't you have to do that again? I don't think it's asking for 2 solutions.
Those are 2 different problems. Yeah, I'm not doing the next problem.
Oh, okay. No. Thanks for being so generous.
Negative log, I mean, maybe I'll make it an F5 or something, of 3.12 e negative 11. And look what we get. I get a pH of 10.506. And not only is that the answer, but look, it supports my very first conclusion. We knew that our pH should be something above 7 because the basic parent was strong. And now we know exactly how far above 7.
All that for freaking pH. 2 seconds to guess.
I'm about to go to
I have a 1 out of 4 chance.
What did you just say? You can't let me scare you.
Honestly, if that was an answer choice on the test, I would just